Okay, so we've got Usain there, and he just ran 100 meters in 9.58 seconds. Is it fast? It's the fastest ever. He's really fast, okay? So just 10 years ago, just breaking 10 seconds or 9.95 was incredible, okay? So now this is unbelievable, okay? So this is the world record for the 100-meter dash. So how fast did he run? How fast did he run? Figure it out. Got a paper, a pen, got a calculator, something like that. How fast did Usain run? So I used scrapping calculator to reproduce his race here. So this is a profile trying to mimic his race as closely as possible. So starting line, finish line. He'll just keep repeating. So this is the countdown here. And there he goes. Okay, so how fast did he run? What's that? 10.4. You should have gotten 10.44 meters per second for something quick and easy. So what does that mean, 10.44 meters per second?
That means he ran 10.44 meters every second.
That means he ran 10.44 meters every second. Is that what he did? He didn't do that, but that's what he told me how fast he went. What's that? That was his average. So did you add up a bunch of speeds and divide by the number of speeds? Well, that's what an average is, right?
If he was moving at a constant speed, he would travel 2.44 meters. If his rate of change was constant, then he'd move 10.44 meters per 1 second.
If his rate of change was constant, he would move 10.44 meters every second.
10.8. If you ran 10.44 meters every second, it would take you 9.58 seconds to finish the 100-meter dash.
Say it louder.
If you ran 10.44 meters per second, it would take you 9.58 seconds to finish the 100-meter dash.
Okay? So we've got this word average, but it's really not, average isn't a great term because you're not adding up a bunch of speeds and dividing by the number of speeds, right? Okay? So we have to make sense of, so what we're calling average speed, this 10.44, we need to make sense of it. That's what these guys are doing, other than an arithmetic mean, like the way you average your test scores. That's not what it is. Okay, so it's not really a great title. Okay, so I'm going to add a new element to the visual here, and then ask you some questions. All right, let's take it back here. So now we're going to have Emma join the race. It's Emma.
Aw, so cute.
I don't know if you can see. Oh, who won? All right, watch it again. His number and her nose. His number on his thigh and her nose. Okay, so a couple of people offered up a meaning of this number, 10.44 meters per second. So I want you to think about it now with the visual and answer some questions here. So you can discuss at your tables, okay? So I got some questions. Discuss through the questions, and then our goal is really to understand what is the meaning of this number 10.44, which we've had some ideas already, okay? Go, so discuss at your table.
Yeah, they travel the same distance.
Just making sure we all are on the same page.
So how many seconds does it take?
Same time.
Yes. Same distance.
So his average speed he like accelerates faster. She slows down. Right. He's speeding it.
He's changing. She's staying. She enters.
Yeah, she definitely moves the speed.
That's definitely wrong.
Yeah.
So average speed, so what it means is,
She's got a constant. So she
the
holding
amount
the
of
average
time it
speed
would
is
take
all.
you,
Well, yeah, she's holding the average speed because it's not showing her. Okay.
she doesn't have an accelerator, she's constantly on.
No, I know that's what I'm saying. They're showing the information, but yes, they're actually animating physically running. And so what is the speed Emma 0 in this
What does that mean?
she's already at a constant speed.
You took
I
this
know,
last
I'm trying to remember how it works.
same amount of constant rate, cover the same distance, the same amount of time.
So your goal at your table is that I've taken you through questions 4 because the goal is question 5. The meaning of this number, average speed. What's the meaning of this number? Could you, at your table, could you come up with a concise and clear definition of average speed? And so there's a reason I'm trying to help you in this animation. I'm trying to help you to make sense of that number, 10.44 meters per second.
I'm sorry, okay.
In the same fashion.
Okay, so maybe let's talk about question number 4. So 1, 2, and 3 should have been pretty easy and straightforward. So number 4, what's the purpose of showing Emma in this animation? Or the way that I've shown Emma, what's the purpose of having her? How about
Showing that Usain Bolt's not going at a constant rate.
okay, to show that Usain is not going at a constant rate. Well, what is Emma doing?
Going at a constant.
She's going at a constant rate, okay? And what does that have to do with average speed? What's the purpose of showing her going at a constant rate?
Well, they're both going at an average rate, but since hers is constant, that's like going the same distance the same amount of time.
Okay.
But not maintaining the constant speed can still get you there at the same time.
Okay.
Don't know.
Other ideas? Why? What's the purpose of showing Emma?
It's showing that Usain Bolt also went faster than 10.44 meters per second. At one point, he went faster than that.
Okay.
So he kind of started off slow.
Alright, you started off slower. Other ideas? Purpose of showing her.
It's just cute.
Well, yeah, definitely.
Just because they have the same average speeds, if you calculate it, doesn't mean that they went the same speeds the whole time.
Okay. What was my original question here? What was our goal? To figure out what? Who is this really about? Is this really about Usain or Emma? Usain. We were calculating Usain speed, right? And you came up with this number, 10.44. But then we said, well, he's not going 10.44. Really? I mean, he's going a bunch of different speeds. So then I brought Emma into it.
She's the speed required to complete that distance in that.
She's the constant speed required to complete that distance in that time. So she's representing the average speed of Usain. She's showing the meaning of this number as it pertains to Usain. You see? So, definition for average speed. I've heard a few. It's really the constant speed needed to cover the same distance in the same amount of time. And that's what some of these guys said. Do you see how worlds different that is from add up a bunch of speeds and divide by the number of speeds? So this word for average is not well picked, okay? Because you're not calculating an average. It's really about constant speed. Okay, so we're going to take this to, we're going to do this worksheet that I just put on your table, which builds off this definition for average speed. So average speed is the constant speed needed to cover the same distance in the same time. Building off of that, we want to just talk about rate of change in general. Rate of change in general.
Can we get one more?
Everybody have one? Okay, so I have a series of, I'm going to run the animation. So this is a typical bar glass, right, for water. Actually, in this class, you know, it might be something else. But, so when I have all freshmen in the class, you know, we emphasize this for water. And, okay, so I'm going to run this animation, and it's going to show the glass filling up, and you see this, that quantity of volume of water in the glass. Oh, darn it. I'll go forward only. Okay. So that quantity of volume of water in glass is represented on the x-axis by the arrow. Okay, so this is view 0. Do you have a couple of questions for view 0? 3? Okay, so discuss as you go. During view 0, you're going to answer these questions and discuss. Okay? So again, we're building off our meaning of constant speed to talk about, or sorry, average speed to talk about rate of change. Now we're just talking about rate of change in general.
So it's just on the table. As long as it's
Right on it.
Oh, I was supposed to have 2 parts.
Nope. Oh, that you got this. You should have that.
I just counted yeah, it goes faster. At the it grows the height is faster than water. It's smaller.
It's wider. It is wider, but
See if you can have that conversation talking about changes in volume and changes in height. So number 2, I'm going to emphasize the second sentence there. Answer that question by talking about changes in volume and changes in height. Specifically small changes in volume,
As the volume
small changes in height.
Height slows down. Yeah.
Maybe this one,
Or
not increase, but like it, the rate slows down,
Yeah.
so it changes. Let's look at the time changes for the volume of the volume. Because the volume is still the same. The height gets
Increases, yeah, I can say that.
Increasing it, decreasing it.
Be careful.
you don't want to say
You don't wanna say that.
Consistent changes.
Sorry.
Consistent changes in volume.
Volume.
in travel less height.
Yeah. It's been a long time since I had Twitter boxing makes me on gigs.
Volume is constant. Height alters dependent on, just kidding. Which point you're at. How do you, it's still increasing, but at a slower rate.
Height, change in volume, and change in height. Who can answer number 2? Talking about changes in volume and changes in height. Changes in volume, changes in height. Anyone give it a chance? Give it a shot? Yeah?
As the volume of water in the glass increases, the height of the water decreases.
Okay, that's true, but you're not talking about changes in volume and changes in height. So think about a bunch of small changes in volume and resulting changes in height. What's going on in those terms?
Changes in height.
Tell me your name.
Melissa.
Melissa, you give it a shot?
We kind of said as the volume in the glass increases, the height of the water increases at a slower rate.
Okay,
So we were trying to word that without time, and that's what we're.
okay. So, possibly a 2 statement, but you're not talking about changes in volume and changes in height. Does anybody know what I mean by that? What's your name?
Crystal,
Crystal, you want to try it?
for equal changes in volume, the change in height decreases.
Change in height decreases. Well, but the height's going up.
But the changes in height are getting smaller.
Right. So as you take equal changes in volume, so it's like you put an ounce in every time. How will the height change? It'll increase. The height will increase. But what about those changes in height? They decrease, right? The changes in height decrease. That's right. Okay. So here so the graph. So if you have for same change in volume, if you have decreasing changes in height, what will the graph look like? Draw it with your finger. Right. So this is view 1. And And so it shows the graph emerging, right? The graph emerging for adding changes in volume and corresponding changes in height will result in the graph of this relationship. Okay, questions 4 and 5. View, or 4, 5, and 6 for view 1. So here's where now we're building off this meaning of average speed that we talked about with Usain Bolt. Okay, so we're building off this meaning of average speed, but it's not speed anymore because there's no time, right? It's not speed. We're building off that same definition.
So the same amount of the same amount of height. Same volume, same volume.
So equal changes.
How do you define 0.052?
You draw it for you. I mean, I know it is, but it definitely or it's something that's constant on the way up. It doesn't straight, yeah. Big triangle.
So number 5 is the important one. Can you write a good definition of that number? Can you write a good definition of that number based on what we talked about with average speed? What does that number mean?
So it's not like the two aren't equal, they're like they might be
You have a second.
equal changes of volume with equal changes of height. The equality
just give a height phrase because it could sound like
You're saying the numbers, you're not saying the numbers,
Yeah.
right? So you're just saying
the changes are
the rate is
like
equal.
changes. Yeah.
Yeah. So instead of using this, for the average speed, so we're covering of the cup. So the range is 5.2. We just like one word out of it. That's why this kind of water. That's what I switched to that. So it's the same, but it takes the two points.
Don't. This isn't about time. But yeah, we're putting in the same amount. So yeah, you can think about putting in the same amount, like an ounce each time. So you're putting in an ounce, an ounce, an ounce, an ounce, an ounce, an ounce. And then we're thinking about how what happens to the height as we do that. Okay, so what'd you get for the average rate of change of height with respect to volume?
0.36 inches per ounce.
So 0.36, is that 0.36 inches per ounce? So, what'd you come up with? What's the meaning of that value? 0.36 inches per ounce is?
Constant height needed to fill the glass, 14 ounces.
The constant height needed to fill the glass with 14 ounces. It's been offered up. How about somebody else? Tell me your name right here.
Raymond,
Raymond.
is the constant rate of change needed to reach 5.052 inches with 14 ounces of water?
He said it's the constant rate needed to reach 5 or so inches with 14 ounces of water. What do you think? Somebody else? I'm not saying right or wrong. I just want to hear lots of possibilities.
Okay, equal changes in volume, outputting equal changes in height.
Equal changes in volume, 0.36 inches per ounce is equal changes in volume, outputting equal changes in height. Does that give the meaning of that number, though? The meaning of that number.
0.36 is the constant height per ounce needed to fill the glass tube, 5.052 inches with 14 ounces of water.
Okay, so one more time. So
0.36 is the constant height per ounce needed to
okay,
fill
let me stop you. It's the constant height per ounce needed to
fill the glass to 5.052 inches
to fill the glass to 5.02 inches
with 14 ounces
with
of
14 ounces of water. That was pretty dang good. That's pretty similar to what Raymond said. Okay? Yeah, so following our constant speed definition, we're talking about an average rate of change. Now we need to, what do we need? We need to achieve a certain height of water, but now we need to do it with at a constant rate. So for every ounce of water, the height's going to go up constantly 0.36 inches, and we'll get the same change in height for the same overall change in volume of 14. Okay, and what about the graph? So the red graph is the constant rate of change. It's a visual representation of this number, 0.36 inches per ounce, right? But every time you put an ounce in, the height goes up 0.36 inches. So it's representing the average rate of change of the water filling the glass. Okay, this is it. We're on view 2. Go. One question. Okay, so ideas, number 6. What would be a practical way to imagine this equivalent constant rate of change?
I don't know if this is like what you were looking for, but the question made me think of like an example. I was thinking if it was like a perfect cylinder.
Perfect cylinder.
Filling up.
Anyone else think of that? Did you mean like this? So the blue graph is showing it's corresponding with the blue height in the actual glass, and the red height showing the average rate of the blue one, so how the water would rise at a constant rate. So think about discuss number 7. Discuss number 7. This is view 3. So that last question was supposed to invoke lively discussion. So what are you thinking about number 7? Talk at your tables. Number 7. Talk. So by glass, we're talking. This is the glass we're talking about. And then, so then, in the end, could you write just a generic definition of constant rate of change for any input and output variable, so or quantity? Suppose you have any input quantity and any corresponding output quantity, not necessarily volume and height. Could you write a definition of the average rate of change? And you're free to talk about it. Yeah. Free to talk about it. Did we do this in 42? Did we do the bar graph in 42? Remember?
Siri and order to
Like I said, to reach an output, it can be anything. But with the input's the hardest part. I know, but that's or that was something this
Okay. Anyone want to offer up somebody new? Tell me your name right here.
Me?
Yeah.
Okay.
What's your name?
Alexander.
Alexander. What did you think? So a generic definition of average rate of change.
I don't know, this is probably wrong, but so for some output, the input varies by some constant M.
Okay. So for some input, the output varies by a constant m. Somebody else. Alfredo.
We came up with the constant rate needed to get the same output given the same input.
Louder.
The constant rate needed to get the same output given the same input.
Constant rate needed to get the same output given the same input. Other, tell me your name. Winona? Change in input with respect to the change in output.
I have the constant change of output needed for equal changes of input to match like a desired outcome.
Okay. Over up here. Chris, what you got to tell?
We had like the constant input of x, outputs constant equal constant outputs of y.
Okay. Any other volunteers? Okay, so it's really the we talked with the average speed, and then we get the meaning when we talked about the meaning of that number, 0.36. That really got to the heart of the definition. So average rate of change. First of all, it's the constant rate of change. Okay, average rate of change is a constant rate of change. To do what? That will achieve an output?
Certain quantity.
Certain quantity? It will achieve the same change in output. It will give the same change in output. So our change in output in this case was a delta H of a little bit more than 5. So it's a constant rate that will give us the same change in output. What's left? Well, it's not, we're not looking at many changes. It sounds like we're talking about maybe many small changes of volume. But really we want to get the same overall change in height for what? Yeah, the same, the given, in this case, change in volume or input. So it's the constant rate that's going to get you the same change in output or the same given change in input.
It's just so hard.
Yeah.
You just know how you feel, and you just can't.
Okay, so let's. Oh, did I turn it off already? Oh, it's down here. So how did this little the little mini lesson on constant rate of change, how did that compare to this little mini lesson on sine x equals 0.5? She laughs. No comparison, right? Okay, so I was trying to give you an example of maybe a better use of visuals. So we had a goal, right? We had a goal. We wanted to learn about average speed, and then building off of that average rate of change. And were the visuals helpful in the conversation and achieving that goal? So that's what it's about. So it's about using visuals to enhance a conversation with a desired goal to learn something. Okay, and so this visual then is what we call a didactic object, and it's all about the conversation that we have. Okay, that's structured by the teacher with the goal of learning something. So let's go back to. I'm gonna go back to the. I talked about the critical précis. So right off the bat, we're going to do one. So if you look in reading assignments, so there is a homework assignment posted, but we're gonna we'll talk about that Tuesday. So I'm going to postpone that. So this one, and I'll just change it right now. It says due this 26th. We're going to push it back. We need more class time to get into this. So that will be due later. That's not due Tuesday. The reading assignment will be due a week from today, and the file is attached right there. So you're going to read. You're going to write a critical précis. Okay. This is a typewritten thing. Again. It's not a reflection. You're not injecting your opinions, thoughts, reactions, responses. You're rewriting the article in a shortened form, shortened version. Okay? So you're summarizing the most important things of that article so that someone would read yours and get the most important, the gist of it. Okay? And then 3 questions. So there's the critical précis, and then 3. These are more reflection type questions. Okay? So that's due a week from today, and you can get started on that over the weekend. And then 2 other tasks. You're going to get graphing calculator up and running on your machine. Okay, you can mess around with it, check the help menu. But we'll get into it on Tuesday. And then also download, print the. We may have a short syllabus quiz on Tuesday. So download or print the syllabus. We may have a short syllabus quiz. on Tuesday. Any other questions? So you have a little work to do, so you can get started on this, do a week from tonight. And we'll discuss that next Thursday.
So
Question?
do you have any kind of like requirements that you're particular about font and size formatting or
No,
anything like that?
not at this point, no.
Okay.
Was that almost a hand? No?
Oh, the vignette, that's inside that file?
This is the actual article you're reading. It's an article, yeah. It's a article about calculational and conceptual orientations. And then you are writing a summary of that called a critical précis, which you can get the details on the Wikipedia. There's a link there. The link's on the, I guess I didn't put the link here, but I put the link on the Wikipedia link on the syllabus. Did that answer it? No, this is totally different. You're going to read an article, so this is about like a research-oriented article, and you're going to write a summary of the article.
Okay, that's what we were confused about, so we didn't know what
You didn't know what?
we didn't know what
Question one.
Yeah, so this is referring to things in the article. You got to read the article, right? Questions are more questions about that article. Yeah, I want one packet. So you're gonna, when you hand me something next Thursday, it's gonna have your critical précis, and then at the end of that, you're gonna have to do 3 question answers. Don't give me 2 separate things. Just give me one thing. Make sense? Other questions?
Just print it out, not email.
So, 3 things. You get started on this. You're gonna print out, download the syllabus, possibly syllabus quiz on Tuesday. Get graphing calculator going. Mess around with it if you want. Okay? Other questions?
Is this being turned in on Blackboard or hard copy?
Hard copy on Thursday.